Hello. Okay, let me explain a few things. In fact, let me explain a lot of things about uniform circular motion. This is all of the basics, all of them, about how things move in a circle. We can discover all sorts of different things about this kind of motion, but first we're going to have some terminology to work with together. The first is this: if we have a circle of some kind, that circle has to have a center. We're accustomed to that. A circle is defined by the distance from the center to the outside. That is the thing that makes the circle, because every point is the point that is a point that is exactly this far from the center. And we're going to call that R. R is the radius of the circle. You may be accustomed to dealing with the diameter, which is the distance across, and that's partly because of the math that made it easy for us to figure the circumference. By the way, that's another thing that we may, at least occasionally, wind up working with, is the circumference, the distance around the outside. But understand this: the definition of a circle is every point that is exactly this far from a single point, the center of the circle. That's what makes a circle what it is. Okay, so now we've got what a circle is. We can move some distance around a circle. Often we move the entire distance around the circle, but we can also move just some of the distance. And if we do that, we can measure how much that distance is in a measurement, an angle measurement. And the character that we use for that is a zero with a line through the center. That's called theta. It's a Greek letter, theta. And it is the angle that we're dealing with around the inside of a circle. Okay. There's one more thing that we'll ultimately wind up dealing with. Yes, the circumference is the distance around the outside of a circle, but we don't always travel all the way around, or sometimes we care about just some particular part of the circle. The distance from one point to another around the edge of a circle is an arc length, and the letter we often use to describe that is S. Why S? I don't know, but S is the arc length. It is the distance that we travel around a circle through some angle. Okay, there's sort of our basic definitions. There's the things that we use to create a circle and to discuss it. And there's a relationship here, and it underpins everything else that I'm going to wind up explaining to you here in a little bit. And that relationship is this. I got confused about this the first time I learned it, just like you guys are learning it now. I got confused to think when I saw that this equation, it's what's written in section 3.1 of the book, that said that the angle is I want to make sure I get this right, the arc length over the radius. I assumed that was a definition, that you can tell exactly how much the angle is as long as you know the arc length and the radius. And it turns out that's not what this definition is. I was glossing over the deltas that are on here. Delta meaning change. Let me write this up here just because we're going to wind up encountering it a lot if you're not accustomed to it yet. This is the Greek letter delta, and it means how much something changes. The change in the angle is constantly related to the arc length over the radius. So this isn't an equation that gives you an answer. This is a relationship that tells you how these things go together. If you were to move around the circle twice as big an angle, but keep the radius the same, that would mean you would cover twice the arc length. That's the way this relationship is set up. If you doubled the arc length, you would be doubling the angle through which you had traveled through the circle. If you triple the arc length, you'll be tripling the angle around which you go around the circle. If you take the radius and make it bigger, make the radius bigger so the circle gets bigger, but you keep the angle the same, then the arc length is going to have to get bigger as well, so that this fraction stays the same amount as the angle is staying the same amount. And probably the hardest one to visualize, bear with me here and see if you can get this one. If this circle were to get smaller, the radius were to shrink, this were to become smaller, but the arc length were to stay the same, stay with me on this. If the radius got smaller, but the arc length were to stay the same size it is, well, then it wouldn't be the same angle, would it? It would have to become a bigger angle in order to accommodate that same arc length with a smaller radius. So if you made the radius smaller, and in a fraction, if you make the bottom smaller, it makes the whole thing bigger. And you kept the arc length the same size, well, then that means this thing gets bigger, which means this thing gets bigger. A larger angle because the radius got smaller with the same arc length. It's all a relationship. It's all interrelated. And remember, one of the big things about a circle is that it's always that shape. And it always has that same big relationship that every circle has. And it's this, that the circumference of the circle is pi times the diameter. That there's another Greek letter, isn't there? Pi. And I'm not going to write the whole definition of pi here because it would take too much space. I'll tell it to you. Pi is that special number that you were taught many, many years ago, 3.1415926, etc. You don't need to know it to that many digits. But pi is a relationship, and pi is the relationship that says if you were to take the length across the circle and pull that length off, and then wrap that length around the circle, there would be 1, 2, 3, and a little bit more of them. A little bit more being 0.14159, etc. Every circle, no matter what size it is, has exactly that relationship. Pull its diameter, wrap the diameter around the circle, and there's a little bit more than 3 of them. That's this. 3.14 of those diameters is the distance around the outside of the circle. And we're going to change that slightly because we don't like to think in diameters. We like to think in radiuses. And it takes 2 of them to make a diameter. And we usually, sorry, I've written that a little backwards from what we're usually used to. 2 pi times r, although it's really 2 radiuses times pi. But it doesn't matter what order you write it in because math don't care what order you multiply in. That relationship is going to figure solidly in just about everything we do from here on out. Now it's a good time for us to step back for a minute and talk about the angle that is the angles that are inside a circle and the way we measure those angles and the way we think about those angles. Let me ask this question first. You should all be able to answer it pretty quickly. How many degrees are there in a circle? Because degrees are the measure that we generally have been using in the past to measure the size of a circle. The whole circle, its whole distance around, is how many degrees? It's 360, right? 360 degrees. And that's worked out pretty well for us. It's an odd number, of course. It's not odd, it's even. But 360 to go all the way around, that's goofy that we came up with it that way. We know that that means half a circle is 180 degrees and a quarter of a circle is 90 degrees. I honestly can't even explain to you why we came up with that numbering system, and we're about to toss it out because we have a better way of measuring the distance around the outside of a circle. Maybe not as intuitive, even though this isn't that intuitive, but definitely better. We're going to change the way we measure the distance around a circle, especially in terms of angles. We're going to change it by starting to think in terms of those radians, in terms of the distance around the outside of a circle. See, if we take a radius and double it and then wrap it around the outside of a circle, and there's pi of those doubled radians around the outside of a circle, a little more than 3 of them, then it's not that big of a stretch for us to say that the distance around the outside of a circle is 2 pi radians. Whatever the radian is, whatever the radius is, there's a reason those two names are so similar to each other. Let me say that again to see if I can make it make a little bit more sense. Remember, we're taking that radius and we're pulling it off and then wrapping it around the outside of the circle. We're doubling it because that's what it takes to make it into a diameter, which is what we're actually wrapping around the outside of a circle. And no matter how big the circle is, tiny or large, whatever that radius is, doubled, there are pi of them around the outside of the circle. 1, 2, 3, and a little bit more. So we could say that you can go all the way around a circle. You can spin all the way around the outside of a circle. You can sweep the entire arc of an entire circle if you go around 2 pi radiuses or 2 pi radians. And that's the angle measure we're going to start using from here on out. The distance completely around a circle is 2 pi radians rather than degrees. That's actually going to help us. It's going to help us a lot as we go forward in thinking in terms of motion around a circle and how fast something's moving. It's angular velocity, and ultimately it's angular acceleration and angular force. Centripetal acceleration and centripetal force is the term we generally use for it. So the distance all the way around a circle is 360 degrees in the old system of measuring. But in our system of measuring, we're going to measure in terms of how many radiuses it is around the outside. And there are 2 pi radians around the outside of a circle. That means there's 1 pi if you go halfway around the circle. See if this helps. It also means that if you went 1 radian, not 1 pi, 1 radian around the outside of a circle, you'd go approximately 57 degrees. If you divide it out, that's what it winds up being. Okay, now that gets us location and place and various measurements of static information. But remember, this is physics. It's the study of how things move. So we need to get into some of the numbers and measurements that we use for movement. And the first measurement that we use for movement is how fast something is moving. What's the speed? We're not just talking about circles. We're talking about things that are moving in a circle. How fast is this thing moving? Now, there is the measurement that we're accustomed to, the one that we've used so many times before, the speed. How fast is it going around the circle, literally from one place to another? But our motion has always been in a straight line before. And we can measure in a straight line. That's not a big deal. We measure how far you went and we divide it by how much time it took. And that's your speed. So linear speed, velocity is the term we usually use for that because we also have a direction. Velocity we've defined before as your change in position over your change in time, right? How far did you move and divide that by how much time it took. Difference here is we can't use a meter stick because that's straight. We need to measure around the outside of the circle. We already have a measurement for that though. It's the arc length, the S. So if we want to know the velocity of this thing that's turning, all we have to do is instead of measuring the linear distance, we have to measure the around the outside of the circle distance, right? That's not even that hard. And if you stop and think about it, say you had a tire that was spinning on a car. If you made that tire roll around 1 time, the car would move forward by exactly the amount that is the distance around the outside of the circle, the circumference, right? So the car is going to move forward 2 pi radians. 2 pi times whatever the radius of the tire is. And we can use that piece of information. We can use that relationship. We're going to create a relationship here real quick that's going to describe the difference between revolutions and how fast they go and radians and how fast they go. And it's as simple as this. 2 pi radians is going to move you through 1 revolution. We can set up any kind of relationship there we need to. If someone asks us, this wheel went around this many times, so how far did that mean the car went? Well, we just need this relationship to say that. We can set up a fairly simple relationship that says, what if you went 10 revolutions per minute? What would be that speed, the radians, the terms that we're using here now? Well, if every revolution is 2 pi radians, then we're going to take that 10 revolutions and we're going to multiply it by 2 pi radians for every revolution. And that's going to tell us that we're going 20 pi radians per minute. See? It's a relatively easy conversion. And in fact, we can use just our standard conversion multiplication method to get our units to disappear, revs on top, revs on bottom, leaving us with radians per minute. And now we have this in angular terms rather than in distance terms. Now this is where we're going to get mathy, and we're going to create something new and oh so useful. You already know this, that the velocity of something is its distance divided by its time, the change in position over the change in time, okay? I want to come up with a new velocity. I want to come up with a different velocity. I want to come up with a velocity that respects the fact that we're moving around the outside of a circle rather than moving some straight line distance. I want to come up with the angular velocity. And the way I'm going to do it is I'm going to create a new relationship that isn't the distance over the time, but instead is the angle over the time. How much angle did you go through in a certain amount of time? It's a much better way of saying it. And I'm going to create an entirely new variable for the purpose of measuring it. Are you ready for this? It is rounded little w. That rounded little w is the Greek letter omega. You've seen omega before, by the way. It's the it looks like this. Nah, nah, nah. But that's a capital omega. This is a lowercase omega. Same letter, same Greek alphabet. It's just that it's the small one instead of the big one. Yeah, they do all sorts of things different in ancient Greece. And it is the angular velocity. That is the angular velocity. It is the speed that something is moving around the outside of a circle in terms of the angular distance, which ordinarily we would say in degrees, but now we're saying in radians. That's the speed that I want, is the angular velocity. So angular, and in this case, I'm going to use the word speed just for consistency. Obviously, it has a direction, but for our purposes, it's just either this way or that way, clockwise or counterclockwise, right? Angular speed is the amount of distance around the circle that you traveled in terms of this angle inside, which we ordinarily would say in degrees. Now we're saying in radians, over a certain amount of time. Okay, that's our new definition of speed for something that is moving in a circle. All right, count how many degrees or how many radians you've gone around the circle. 2 pi if you've gone all the way around. And divide that by how much time it took, and you have the speed that the thing has moved around the circle. Cool. I need a way to relate these two, and I can come up with that here. If I take this delta theta equals delta S over R, and I solve it for delta S, and I plug that delta S in here. So now I have theta over delta, that's delta S is what goes up there. So I have R times theta, okay? And then I solve that for theta, and I put it in here, and I divide those out and create the relationship there. The delta t's wind up canceling out, and I create a relationship between linear speed and angular speed for anything moving in a circle. I can create a relationship that says I know how fast I'm going forward if what's going forward is spinning in a circle. What's its angular speed? And that relationship is this. The linear velocity is the radius times the angular velocity. And there's another one that's going to wind up becoming important. The angular velocity is going to be the linear velocity divided by the radius. I can convert between the linear speed that a car is going and the angular velocity that its wheel has as it's spinning in that direction. And it's an easy conversion. I just have to have the right one of these and plug in the radius, because the radius is actually the thing that decides what the relationship is between them. I promise you, this is as deep into the math weeds as this gets. From here on out, it's much more conceptual, and there's a couple of more simple pieces of math. You'll like them when we get there. Things move in circles, but they don't move in circles because they want to. Newton was actually very clear about this. He explained that everything that moves wants to move the way it is from here on out. That was Newton's first law, the law of inertia. It says that if something is moving, it will continue moving in a straight line until something acts upon it, or it will stay at rest unless something acts upon it, which means it's moving in a straight line with a velocity of 0. Straight lines, that's the important bit. You can't get past that. Something that's moving without some external force acting on it will continue moving in a straight line. So for this to be moving in a circle, even though it feels uniform and feels like, it's just doing it on its own, something has to be forcing it. Something literally has to provide a force on the thing to make it spin in a circle. Otherwise, it would continue moving straight. We can prove that actually by spinning this around and then snipping the rope and watching what happens. It doesn't continue moving in a circle. It moves off in a straight line from that moment because the force has been removed. So what's providing the force? Well, in every situation, it's a different thing, but something must be providing that force. And I hope you recognize that in this particular example that I'm spinning right in front of you, what's providing the force is the string. The blue thing here has tension in it. It has tension because I'm holding it from the other end and preventing it from moving along. Actually, it's the mass of the object on the outside of the string here that's wanting to continue moving in a straight motion. But by providing tension to fight it from the center, I'm forcing it to move circularly. Now, it's not exactly uniform. You can see my fingers moving up and down. I'm having to give it a little bit of a boost to keep it doing it because of friction and because gravity's fighting me on the way up. But the reason this is moving in a circle is because I'm providing tension through the string. And that means a force. And for there to be a force and a mass means that I can measure how much this is changing. I can measure the change in motion. And this is an important detail to pick up on if you really want to deeply understand this. I'm changing, by holding onto the string, the velocity of the object on the outside of it. Now you might say, wait a minute, Mr. Gear, you're spinning that at a pretty constant speed. It's going around and around and around, and it's not changing how fast it's going. But I am changing its velocity. Let me see if I can explain that here. At this moment in time, let's say the moment that it just flew off of the string, this thing wanted to be going straight. And when I cut the string, accidentally, it continued going straight from there, like it wanted to. A moment later, though, let's say a moment before, while it was still attached, it wanted to be going this way. At every moment in time around the circle, it wants to be going straight, but straight is a different direction at every moment around the circle. And that's the important bit. Something must be changing its direction, and that's changing its velocity. Because remember, velocity has two parts to it. Velocity not only has magnitude, how much, how fast, but it also has a direction. And because I'm constantly, through the force on the string, changing the direction that this thing is going, I am in fact changing its velocity. And when you change something's velocity, you are providing it an acceleration. I am accelerating that object around the circle. And this is the fun part. I'm accelerating it towards the center of the circle. Centripetal acceleration. Centripetal is just a big $10 word that means towards the center. When something is spinning in uniform circular motion, we've already established something must be forcing it to spin. We'll get to that in a second. That force is creating an acceleration, always toward the center. And it's that toward the center that keeps this moving in a circle instead of flying off straight like Newton told us it wants to. And we can represent that acceleration. We can tell you exactly how much it is. We have a way to measure it. We have a way to represent it mathematically. The way we get to that mathematics requires some impressive geometric calisthenics that aren't really important right now. If you're interested in finding this derivation, they run through it perfectly in section 6.2 in our textbook. I'm just going to go ahead and give you the formula, two of them, that describe centripetal acceleration. Here's the first one. Take the linear speed and square it and divide that by the radius. That will tell you the acceleration that the object on the outside of the circle is experiencing for the purpose of having that circular motion. But that's in terms of linear speed, how fast something's moving along the outside of the circle. I'd also like to have it in terms of my angular speed, and fortunately we've got a formula for that as well. The centripetal acceleration in terms of angular speed is the radius times the angular speed squared. Either formula will work. Either formula will tell you exactly the same amount of information. It's just that one of them is in terms of the linear speed, how fast the outside of the tire is moving, which, remember, is exactly equal to how fast the vehicle is moving forward that's attached to the tire that's spinning on the ground. Or the centripetal acceleration based on the angular speed, which is how fast something is turning around. Which one you use depends entirely on which piece of information you know. Do you know the linear speed? Do you know the angular speed? Do you want to know the linear speed, but you know the acceleration? Do you want to know the angular speed, but you know the centripetal acceleration? You use the formula that's appropriate to the units that you possess at that moment. And you can use those to determine exactly what the acceleration is toward the center. Remember, this isn't acceleration that is making something move faster. This is acceleration that's making something change direction constantly as it moves around the outside of the circle. We're almost done. I told you the last part would be easy, and I think it is. It's also tying everything that we've talked about here together, because remember when we first started discussing this many minutes ago, we talked about how something's moving circularly like this. Something must be forcing it to move circularly like that, right? So there is a force. In this case, there is a tension on the string that's holding the mass on the outside. That's a force. Or if a car is turning along a curved road, something's making it turn. And of course, you think that's the steering wheel, and you're not wrong. But what's really making it turn is the friction on the tires that have been turned a different direction from what they were traveling before. That friction is providing a force that's pushing the car into the turn, centripetally towards the center of the turn. If you've ever heard anyone talk about designing curves on roads, they talk about the radius of the curve. Literally, where would the center of the curve be? Somewhere out in space, out in the middle of the cloverleaf interchange or whatever. And that is the friction on the road is what's causing that force in. Everything that's moving in a circle has some force that's causing it to do that. And that is the centripetal force. And we can measure that as well. We can measure how tight the string is as it's being spun around. And we know that if we spin it faster, we're going to get even more force that's pulling it out. Or we know that if we spin it at the same speed and we change the radius, that changes how much force there is as well. We need a relationship that states that. And fortunately, it's easy. It's easy because Isaac Newton, once again, made really clear for us what force is. Do you remember Isaac Newton's second law? It was the simplest one. It was the math one. It's that force is mass times acceleration. Well, this thing obviously has mass, and that's not hard for me to measure. I can put it on a scale. That's easy to deal with. The only other thing I need to know what that force is the acceleration. If only I had some formula that's telling me what the acceleration is in this circle. Oh, wait, would you look right there? So if you want to know the centripetal force, again, there are going to be two formulas for it, depending on what you know. We'll do it for the linear speed first. If you know the linear speed, which means you can figure the centripetal acceleration using the linear speed, it's going to be as simple as the mass times that acceleration, velocity squared divided by the radius. That's if the linear speed is the thing that you have information on. If you want to know that centripetal force, but what you know is the angular velocity, it's the same piece of math. It's mass times acceleration. Only this time it'll be that acceleration, the radius times omega, or the angular velocity, squared. Simple as that. You want to know how tight this string is, what the force is on it? Well, all you're going to have to tell me is how fast this is traveling around the outside and the radius, and you've got it. As long as the mass, the radius, and the speed around the outside. If you know how fast this is spinning in terms of revolutions, remember we can convert from revolutions to radians to figure out what the angular speed is, then you can use this formula. You take that angular speed times the radius, once again times the mass, and that'll tell you how tight this string is. It will also tell you how much frictional force you must have on your car to get it to have that turn. It'll tell you how much force you're pushing against the outside of the carnival ride as you're being pushed up against the back of it. You feel like you're being pushed back. There's a force that's pushing you in, and it's the equal and opposite force. You can figure out exactly what it is. Centripetal force. Remembering, as I hope we do, that the AP Physics test tends to not care so much about tell me how much this would be, tell me the answer, 6.72 or whatever it is. Instead, it tends to ask us about relationships. Let's talk for just a second about what this force thing means then, and about the relationship that we've created here, how things change if you change things. We know that there is a force in this string as I'm spinning it around, and it's a certain amount based on the velocity and the mass and the radius that I have right now. What would happen if I doubled the radius? How would that change the force? Well, let's take this example we have right here. If we double the radius, but we keep the spinning speed the same, the speed at which it's traveling around the outside of the circle. Well, that means we're going to be using this equation rather than this one, because the linear speed around the outside, the arc speed around the outside, is staying the same. The radius, however, is doubling, and of course the mass is staying the same. Radius in this example is on the bottom of the equation, so when I double this, it doubles the denominator, and that means it's going to cut the whole value here in half. Double the radius on this, but keep its velocity around the outside the same, and the force is cut in half to keep that same circular motion. What if we double the mass? That's the easy one to figure out, right? If I'm spinning this around, but I suddenly magically made this twice the mass that it was before, twice the mass, but the same velocity and the same radius, well, it's going to take twice the force in order to keep it moving in that circular motion. Simple. What if I take this, spinning it, and I suddenly double the speed that it's traveling around? Now remember, double the speed that it's traveling around the outside of the circle. Once again, I'm on the linear version of the force measurement, the force equation. Double it, but you'll be squaring that doubling. And according to the factor of change method of figuring things, that means I take this number and double it, but square it, I get 4. The radius is staying the same, call it 1. The mass is staying the same, call it 1. I wind up with 4 times the force. Double the speed that this is spinning around, and it is 4 times the force on the string, and much more likely that it'll break, right? I can do those analyses just like that with this version of the formula as well. It's just that this time I'm not measuring how fast the thing is moving around the outside of the circle. I'm measuring how fast the circle is changing, the angular speed, which is in radians per second, kind of like degrees per second. We're really measuring more like it's RPMs rather than, that's a particular kind of unit, rather than its speed that it's traveling. We're measuring its angular speed. So if I was spinning this a certain speed, and then I doubled that speed, once again, double the speed is going to be squared and mean that I need 4 times the force. That makes perfect sense. Double the mass, I'd wind up with double the force as well. Double the radius, and I'd wind up with double the force as well, but only if I keep the angular speed the same. If I double the radius, but keep the angular speed the same. Think about it though, that means that it must be moving significantly faster through the air, because I'm talking about it going around the circle in the same amount of time that it did before. But by doubling the radius, I've made the circle so much bigger, right? This is how it's confusing how these things interact. I double the radius and keep the angular speed the same. Well, that must mean that it is traveling a much greater distance in the same amount of time. And this would have worked out with a different velocity, whereas this velocity would be staying the same. The angular velocity is measuring the amount of time to go around the circle once. The linear velocity is measuring the speed of the object as it travels through that arc in space. So both of those measurements wind up giving you different relationships based on what you know. But ultimately, you use the one that's germane to what you know. You know the angular velocity? Great. Use the angular velocity formula. You know the speed at which this thing is traveling through the air, or the speed that the car is traveling along the ground? Then you use the linear velocity one. Okay, I've talked enough. That's uniform circular motion, all the way from defining our units and our variables and such, all the way up to finding the angular velocity rather than the regular velocity we're so used to, switching back and forth between linear velocity and angular velocity, and using those terms to find the centripetal acceleration, the rate of change of its direction as it goes around the circle, and ultimately getting that to the thing we'll almost always ultimately want, which is the centripetal force. How much push is being applied in order to create that uniform circular motion. Hope you get it. Get in and try the problems now. Remember, you've got answers available to you, or I can give you answers if I haven't given them to you. Ask me questions if you need. I hope it makes sense now. One more thing. If you haven't been taking notes all along, now might be a good time.